Welcome back to Differential Calculus. In this video, I want to talk briefly about some ideas related to transformations of graphs. Once again, this is a skill that you should be at least somewhat familiar with. The big ideas here are just to remind you that it is a thing that exists, because I know in my experience teaching courses like pre-calculus or college algebra, this is one of those skills that every student kind of sort of gets through for the exam and then hopes that they will never see again. Unfortunately, it's actually one of the most useful skills that exists for a number of reasons, none of which we can really clearly see in class, but that doesn't mean that they aren't there. As an example, one of the things that I spend a lot of time with is writing computer programs to do numerical calculations for me. And one of the really nice tools of numerical calculations that I like to use is the Monte Carlo method, which involves random numbers. A general random number generator will give you a number at random in the interval from 0 to 1 with precision based on the particular programming language you're using and the particular computer you're using. If I want an interval from 0 to 1, or if I want a random number from 0 to 1, that's great. If I want a random number that goes between -5 and 5, well, then I have to do some work. I have to figure out a way to do a transformation that will give me a range that is still interesting. And so being able to think about transformations of graphs, being able to think about how they relate to the range is the tool that I need in order to figure out how to write the function, the random number generator, that I actually need for the problem that I'm trying to solve. We're not going to get there in this course. We're going to look at things very much from the other perspective of when there is a transformation, what is happening. Because quite frankly, even though it is boring, it is far and away easier. You spend enough time on this, you will start to understand how it works, and then when you have to do it yourself, you're going to be in a much better situation. In general, what we're looking at is if we know what the picture y equals f of x looks like, can we figure out what the picture of something more complicated, y equals a times f of bx minus h plus k? And that is every bit of complexity we can possibly put into this. And I have, if I can push the right button, I have prepared something in Desmos for us on just that. You can see here that I have this folder called mystery functions, so you can't tell what function I'm working with. And I have graphed, you can't see it right now, but I think that's orange. I may have mentioned I'm colorblind, so I'm color coding things and I have no idea what I'm doing and I have no idea if it actually works. But you can see the dotted line in orange gives us our original function y equals f of x. This line, which I think is supposed to be blue, is our transformation. And I have chosen a equals 1, b equals 1, h equals 0, k equals 0. That doesn't do anything at all. And all I'm going to do is sit here and play with these sliders and look at how the transformation changes. Let's start with a. If I make a number larger than 1, it stretches the graph out to be taller than it was before. If I make my way back down and get that set back to 1, we've matched back up. If I choose a value of a smaller than 1 but bigger than 0, I get things that kind of look like they are flattening out. And unfortunately, this doesn't work very nicely linearly. It is an exponential scaling. When you go from 0.1, it still looks like the same function, just flat. And then when you get to 0, it is a flat line. But that is a nice and important transition point because from there you can go on to the negative values. And let's jump all the way to -1. At -1, I have taken this function and flipped it upside down. Negative numbers bigger than that will stretch it out. Negative numbers between 0 and 1 will flatten it, but negative numbers flip the function upside down. Let's go back to +1 and move onward. The parameter inside b, we don't use all that often except in trigonometric functions. Right? Most algebraic functions you can rewrite to get rid of this b. Right? If you're dealing with a squaring function, you can factor the b out and just square it, and so nothing really is happening. But when you have small values of b, it is going to stretch the graph horizontally. When you have values of b larger than 1, it is going to shrink the graph horizontally. I'm not going to deal with negative values of b. It will cause flipping to happen, but it's a little bit harder to follow, so let's just not worry about it. H is a translation horizontally. It causes the graph to move left and right. One thing to notice here, I have this set up so that when you take a negative value of h, it moves to the left. When you take a positive value of h, it moves to the right. But there is something happening. In the original equation that I'm graphing here, there is a minus sign in this. And it is really easy to forget about that. Whenever you have something going on, you have to be paying attention about the fact that that is a minus sign and allowing that to work in your favor. Contrast that with the k out here that has a plus sign on it. And the k controls the vertical displacement upward and downward. All right, you can do all of these things at the same time in the same graph if you are so inclined and really make a complicated mess of things. We try to avoid doing that. Right? In practical applications, the fewer parameters we have, the better our life is going to be. But having two things going on at the same time is always important. All right. I have changed things around a little bit here to give us a periodic function to play around with. The controls work much the same. The reason that I like using this function is because it has a more interesting domain and range. There is an upper and lower bound to the graph. And so one of the things we can do is track what happens to that upper and lower bound as we perform our transformations. If we have a value of a, it will stretch and move the upper and lower bounds together. If we change the value of k, I have a wrong thing happening here. There we go, quick debug. If we change the value of k, it will cause those two bounds to slide in tandem. And so if we want to do something like say, we want this function to be transformed to have a range between 0 and 5, we can play around with h and k together and get something that more or less works, right? Doing this algebraically, thinking about how that transformation is going to happen to the upper and lower bound will give us a more precise value. But it's an idea that we can work with. It's something we can use as a starting point. And that's, again, the value of working with transformations on graphs. And that's one of the reasons that I want you to be able to think through this. All right, so let's get back to my notebook and let's take a look at a quick example of that. Here is a simple piecewise function. F of x is 0 if x is less than 0. F of x is 1/4 x if 0 is less than or equal to x is less than or equal to 4. And f of x is 1 if x is greater than 4. I can jump over to Desmos really quickly and graph that piecewise function if you are so interested. But the interesting question is going to be here, what happens on a transformation? Right? So if I transform this graph, and I want to look, instead of at f of x, I want to graph y equals 2 times f of x minus 2, I'm sorry, 2 times f of x plus 2 minus 1. What is that going to do to the graph of the function? Well, we can think about this algebraically piece by piece. Y equals replace x with x plus 2, multiply the result by 2, and then subtract 1. Right, so 0 times 2 is 0, minus 1 is minus 1. But now instead of x less than 0, we have that x plus 2 is less than 0. Right. In the second piece, replace x with x plus 2. Then we have 1/4 of x plus 2. We want to multiply that by 2. 2 times 1/4 of x plus 2 minus 1. If 0 is less than or equal to x plus 2 is less than or equal to 4. And then we have, well, 2 times 1 is 2, 2 minus 1 is 1 if x plus 2 is greater than 4. And suddenly this has gone from something fairly simple to something incredibly difficult to read. But if we take our time and we simplify each of these things, if x plus 2 is less than 0, that means that x itself has to be less than negative 2. If we multiply out, 2 times 1/4 is 1/2. Distribute that, we have 1/2 x plus 1. I'm sorry, yeah, 1/2 x plus 1. And then I forgot to subtract the 1 when I wrote that down, so let me fix that real quick. That's not my eraser. That's my eraser. We get just 1/2 x. Solving the inequality, I get that negative 2 is less than or equal to x is less than or equal to 2. And I get my result there. And so my graph goes, my original function looked something like that, with key points at 0, 0, and 4, 1. My transformed graph is going to be the same sort of thing, but instead, it's going to have key points here at -2, -1, and at +2, +1. So we have stretched the graph out, we have shifted it down, and we have shifted it over. When you are fluent with transformations of graphs, you can look at just the description of the function that we started with. And you can say, okay, that is going to stretch it twice as high. It's going to shift it down 1. It's going to shift it to the left 2, and use those instructions to sketch out the graph without having to go through all the intermediate stuff. If that's something that you're comfortable doing, I strongly encourage it. If that's not something you're comfortable doing, well, Desmos is a thing. I encourage you to get comfortable using that and starting to play around with transformations of graphs. It's just a matter of taking the time, getting used to it, getting used to interpreting things. If this is something that you've not been comfortable with when you're looking at the homework problems, go to Desmos, type in the original function, type in the transformation, see what happens, and use that to your advantage. I will tell you that it is very likely on an exam that I'm going to give you something that involves a transformation, but you don't know what the original function is as something you could type into Desmos. You have a graph to start with and playing around with that. So getting used to thinking about where the transformation is happening, what is happening to the graph, and doing it pictorially without the algebra is the skill that I want you to start cultivating in this course. The last thing that I want to talk about today is the idea of symmetry. There are several symmetries that can exist. The two that I care about are even and odd. Algebraically, the definition of even symmetry is that f of minus x is equal to f of x. The definition of odd symmetry is that f of minus x is equal to minus f of x. But I want to think about this graphically. A function that has even symmetry is mirrored on the y-axis. It looks like it is its own reflection. The fact that this is called even is not a coincidence. The poster child for even symmetry is an exponential or power function with an even exponent. Odd symmetry is not something you're as accustomed to geometrically. The way I tend to think about it is it's a graph that is mirrored 180 degrees. And once again, the name gives it away. A function with an odd exponent, a power function like this, y equals x cubed, always has odd symmetry. Oops, I wanted a different color pen for that. But think about twisting this graph half a turn. If you twist the graph half a turn, it gives you the same thing you started with. That's what we're talking about when we say odd symmetry. So if you know the graph, you can figure out symmetry. Or if you can figure out symmetry, sometimes that makes it easier to come up with the graph. Helps if I write the problem down right. Consider, for example, the function f of x equals x squared minus 1 all over x. If I want to test to determine if this function has even or odd symmetry, I'm going to evaluate f of the opposite of x. Now, if I take the opposite of x and I square it, that just gives me x squared again. In the denominator, I just have the opposite of x, which means I have this extra opposite hanging around. I can bring that in front of the function. The opposite of x squared minus 1 over x. And now that I've taken that opposite out, I have exactly the thing I started with. This is the opposite of f of x, which means that this is a function that has odd symmetry. Here's one that is related to that. G of x is x to the fourth over x cubed plus 1. And my question to you, is this function even or odd or neither? And one thing that I should point out before I wrap this up, it is the case that most functions are neither even nor odd. Most functions do their own thing. Whenever you do have even or odd symmetry, though, you have a lot of information that you can use to analyze the function more quickly, save yourself a lot of time and headache. A lot of the things that we're going to be looking at in this course, if you can quickly say this is an even function or this is an odd function, you can save yourself half of the work. Right? So with those thoughts in mind, take a look at this function, try to determine even, odd, or neither, and I'll see you in the next video.